Okay, let's get started. We are going to do lecture 9 and 10 today, and it's going to cover the second part of object orientation. Really, we've seen it all already because I talked ahead on the last video, or the last lecture I did. But now we'll see an example, kind of refresh your memory, put all the pieces together, and then lecture 10 is all about comparing object orientation, object-oriented design with structured analysis. And that'll kind of put the pieces together in terms of why we do both. And then that'll be enough for one day. That'll be enough for today. So let's see what we got going on here. Let's see. So the requirements. In terms of the long term, what are we looking at? In terms of your projects for this course, we know what happens at the end of the semester. Well, probably not going to. Well, actually, I've had some people implement projects that they've created or ideas that actually ended up getting implemented, because usually they borrowed something from the company they were working at or something of that nature. But it is actually kind of nice to see all this work happen and everything that you're doing actually turn into a project. But for you, for the purposes of this course, you're not necessarily going to have anything that you're going to do anything with at the end of the course. Instead, you're probably going to just chalk it up as a learning experience and never visit that topic again until you have to do another term project and then use the same topic over again because you're familiar with it already. But in the real world, what we're looking at is preserving the work that we've done, being able to utilize that in the implementation and in the development, and be able to take that and actually make a marketable product out of that. And so requirements, design, and implementation are all supposed to work together, which is why you spend a year and a half or a year putting together a requirements doc, a design document, and all of the architectural diagrams and things that we're putting together. And looking in terms of reusability from future projects. If you're a software engineering firm and you've done all this for one project, you're gonna hopefully the next time around it's not going to take you as long, and hopefully you'll be able to do a better job, and maybe you'll be able to reuse some components or reuse some thinking that you've done. In terms of remembering the definitions, and what the slide is showing you, what the requirements is supposed to be giving you is the what, the design is supposed to be giving you the how. And keeping that in focus, we could come back and look at the hows from the whats and compare how some implementations may have been better than others, etc. In terms of what the requirement specification actually is, it's a specification in terms of the nothing outside of the what. So our analysis that leads into our design is supposed to be teaching us the how. And we're not supposed to think about it ahead of time until we've done the analysis, and then we come up with the how in terms of what we're implementing. If we take the what and we apply it to an object-oriented methodology, what we end up having is kind of a structured way of going about developing the how in terms of the solution to the problem. And object orientations we've seen so far, we're modeling objects from the basis of what the methodology entails, and then we take those objects and we show different characteristics about the objects. The object is the class. So from the object diagram, we created a class diagram from that, where this part 2 of object orientation, this particular lecture, kind of gets into the concept of taking and actually looking at the implementation details from a design perspective. So we're taking our analysis and we're actually implementing the design right now in terms of the class diagram, in terms of the sequence, the hierarchical, all these other specialized diagrams that we're making from the object. And as I mentioned previously in a couple weeks back, hopefully I mentioned it, just because we're doing an object-oriented analysis approach, we don't necessarily have to skip systems analysis and design or structured analysis. We can still do that. So it's really common to do a entity relationship, a data flow, and then start doing your object-oriented diagrams, only because it gives you a more complete picture. One methodology doesn't solve all. So given a real-world scenario, you pretty much have to decide on classes that you're going to use for the system, and this lecture takes it from the object approach and creates a class diagram in a very similar manner. So what you're going to look at is a noun extraction approach, which we've already seen, but that was in relationship to objects. Now we're kind of focused on the classes to extend the concept a bit further. What terms do the users and the implementers use to describe the system? Those end up turning into candidate classes. If you say, I have an accounting system, and my accounting system has a reporting module. So it's very common to call the system an accounting system, and we have a reporting module, receivable modules, payroll modules, all these different modules. Could be classes, could be abstractions of classes. So a lot of developers actually take that approach, because then the end user can actually say, look, we've implemented the reporting module. Here it is. It's the reporting module you asked for. And then each candidate class can be specifically defined now if we take it a bit deeper. So before we were looking at object diagrams, now we're looking at taking and defining each one of the classes and looking at the identity states and the behaviors that are associated with it, and actually developing the interaction that these classes are going to perform. Each class may also have a set of responsibilities, as we saw before. And this kind of goes back to that CRC concept, the class responsibilities and the collaborations, which is the identity state and the behaviors, apparently. If you translate it into different terminology. But the responsibility would definitely be something that the class is supposed to be doing, and otherwise it doesn't really have an existence. We shouldn't have classes in the system that don't really do anything. We should X those out, get rid of them. Otherwise we have wasteful, inefficient code. The responsibilities, another thing that we have to look at is, are they evenly balanced among the classes? Or do we have one class that's doing all of the work and none of the other classes are doing anything? So we can load balance our responsibilities among all of the different available classes, which is not a bad idea either. And then also considering what attributes and operations does each class carry out in terms of what it's accomplishing as well. So here's that noun identification example again. So humor me for a few minutes as we go through this. I don't like this approach actually, because it doesn't, it's like here's our identified nouns. I think it just creates too many classes to start out with. But some people need some sort of a methodology. Math people, they need a structure to what they're doing. You can't just guess at it. There has to be like a pattern or a method to follow. So this is the one that's actually the most commonly practiced method for the most part. So library in red here. Oh yeah, it does show up in red. That's good. Contains books and journals. So we have library, books, and journals, and we have candidate classes that come out of this. We saw this. This is the same approach that we're using to create an object. Object diagram. We use the same approach to establish or to create a starting point for the class diagram as well. So we have library, book, journal, copy, and all these little things here. Then this should be over here. There's an extra space here for some reason. And the name of the system, the event, these are just some descriptions that may end up being properties in the long run. And then we look at the relationships between the classes. We say a book is an item, a journal is an item. Well, we have items. We have a lot of items. An item is an item. Here we have item. Well, library owner. So, is item really needed? Not really, actually. An item is an item. Well, a book is an item and a journal is an item. So we start looking at the logic of the candidate list that we've created. And then we can start scratching items off the list to figure out which ones may or may not necessarily be duplicates. And then we take a look at the operations, going back to the class responsibilities, the operations, the data that's going to be holding. And then we look at this and we say, well, a library member borrows a copy, returns a copy, member of staff can borrow, return. Items not really needed then in terms of the concept. So we can decide to scratch item off of the list. And what we'd end up doing is taking this big list and we shorten it down after looking at, all of these different nouns. Because, the description could be repeating itself. It could be talking about different things that are all the same item, So in this particular example, item was really the only thing that we could possibly scratch out. But we start with a big list and we narrow it down to smaller. And then we build the first iteration of the class diagram. In this particular example, we have a member of the staff that is, that works with the library member, is a member of the staff. And we have a journal, a copy, a book. A copy is a copy of a book. And it looks like an entity relationship diagram. It looks like an object diagram. Looks like a class diagram. It's actually all three. But there's different levels of detail. In the class diagram, as you notice, now we start breaking the boxes out. And if we were to take away these lines right here, and we had open boxes and we just put the word library member in there, we would have both, actually with cardinality and everything here, we would have both an entity relationship and an object diagram. Because we've put the lines in here, we're calling this a class diagram. Because we could put in the other two components, and then what we have is there the identity, the states, and the behaviors that belong in these three different boxes. So we have the identity, that's as far as we've gotten. So it's very common to see it written out like this, because then what you can do is use that as a starting point and say, these are the classes that I'm intending to put in here. Because what we could do is add classes, like controller classes and stuff. And I think we covered that in the last lecture. And after we've looked at this and said, well, what's missing in terms of the functionality? And then in some of them, we might actually put in some states and some behaviors, given, you know, what we're looking at. So let's take a look at the rough sketch of a wholesale system. So a wholesale merchant supplies retail stores from stocks of goods in a warehouse. What classes would you use to model this business? And this is kind of the type of questioning that you'll end up getting in terms of like maybe the final exam or something. You know, like, and it's kind of a common question. Like, well, you know what? It's a wholesale merchant, and he supplies retail stores from stocks of goods in a warehouse. Well, we got a retail store, merchant, order, product, shipment, invoice. These are kind of items. You can take and pull the nouns out of there if you want. Wholesale, merchant, supplies. We end up with a bunch of retail store, merchant, order, a bunch of odd nouns that we've pulled out of there. And then we can kind of like look at it and say, well, retail store, what information, what states would we have for the retail store, and you know, we could start filling in the boxes essentially. How we're gonna locate them on the screen. This kind of changed in terms of the order a little bit. We can reorganize a little bit and say, well, retail store, we only know there's going to be a name, an address, contact, financial information. And reversals, those would be returns. You know, well, we're going to have damaged goods, return, wrong item. You know, shipment is going to have this stuff. And the responsibilities could be, you know, tracking status of shipment. So we could put responsibilities in here. We could put method calls in here. It doesn't necessarily have to show up in this particular form, which is what this slide is pretty much showing us. But it's interesting that they've added another box to here. You can put any information you want inside this box. It's not like a set in stone. It has to have those three components. So in this particular box here, we have methods, we have states, and here we have responsibilities. And we have 1, 2, 3, 4 sections instead of 3. Optional, I should say. Which tells you there's no standard and object-oriented design either. People just do what they want. So we can expand the class by modeling, let's say, modeling the financial information. Up here we had some financial information over here. So we could say, well, the retail store has an association with a transaction. Well, the transaction usually occurs at the retail store, and it involves a payment and an invoice, perhaps. So which class is responsible for the financial records for the store? Well, the diagram doesn't actually show you. So you could put something in there, add something in there, or specifically specify. So the point I'm trying to illustrate is that it depends on what you're trying to show in the diagram as to what level of detail you're going to put in the diagram. And you would probably put a caption above or below the diagram saying, you know, this is going to show the financial, this is going to show like the financial records or something. And here's modeling the invoice. We have this kind of a question mark going on here because we have the retail store that has an invoice, and the invoice has got items from a parts list. So if it's this manufacturing of this auto retail manufacturing company, and we have a shipment that's associated with the invoice. But how do we know what shipment is from what store, or do we care? So we have this big question mark going on here between. And this is something we might put in the diagram to take back and show the user and say, well, we have a retail store and we have invoices because we have purchases. Let's say, you know, and actually as a classic example, you know, you ordered it online and it's a chain and there's stores throughout the entire United States. You're in California. So what store are they going to ship it out? Hopefully they ship it out of the California store, but it might not. The shipment might not come out of a California store if the item's not in stock there. And what do you care? It's being shipped to you. So it could go out of Colorado or something, or Arizona, or another local neighborhood state or something. And here we have the plus and the minus in terms of the private and the public. If we wanted to take it a step further, we could indicate with our methods down here whether or not we're going to make them part of the public or part of the private interface. And again, this kind of goes back to, well, if you've got some object-oriented programming experience, you know about public, private, and protected. And if you're the one drawing the diagram and the audience for this diagram is somebody who is going to be implementing this and not, like, let's say, the customer, then we can say, you know, goods shipped is going to be a public thing method, and then send an invoice is going to be a private method that's being run within this class, this invoice class, and we're not going to have exposure to it outside of this class. And we can kind of indicate in the diagram, depending upon the need, what it is we're trying to show. Those different types of scenarios as well. So lessons learned, there's no single correct design. And we should probably highlight that, put it in bold, underline it. During the design process, elements are going to be hidden. Even if you take an object-oriented design approach, and as we've seen here, there's no standard. You know, we're going to put the public and private in here. We're going to actually show this correlation. And the downfall to this entire methodology is that we're only showing what it is we're intending to show. We're leaving out a lot of information. And this is where we go back to and we say, well, the entity relationship diagram is going to show everything. It'll show more, but it doesn't show the same level of detail. So here we have, you know, the ability to add stuff to the entities or to the objects and actually show associations instead of relationships. And we're able to show them in a lot more detail, in a lower level of abstraction, what's going on. And it adds to the complexity, but it also takes away from the big picture as well sometimes, depending upon what we're showing. So elements might be missing, they might be hidden, and the model may not be consistent. So the diagram is not the whole design. Diagrams must be backed up with specifications. So we take, normally with an object-oriented approach, we rely more on the requirement specification than we would in a structured analysis approach, because in a structured analysis approach, the diagramming that we're doing is mimicking, or it's strongly built on those requirement specifications and those specs. And so we don't necessarily have to keep flipping back and forth. We can actually take a look at that entity relationship diagram and kind of, you know, kind of see a big picture of the entire system. So in object orientation, you do that entity relationship, you do that data flow for the same kind of similar purpose. So you don't have to go back to thousands of pages of requirement specs. You can see it. You can see those thousands of pages of specifications right there in the diagram. And then you have your supplemental object-oriented ones. So that's why I'm, you know, kind of reiterating the point that it takes a lot of different levels of abstraction, and it takes you know, combination of a lot of different types of approaches to actually get a complete design from it. So levels of abstraction. So the complexity obviously depends on the level of abstraction that we're looking at. The more detail, the lower level of abstraction. The fewer details, the bigger the picture, the higher level. So imagine yourself on a helicopter coming down and up. You can't see the ground as clear as you can when you're sitting on top of it, and you're inside of it, or you're on top of it. And that would be a very low level of detail. So low levels of abstraction are needed for implementation. Higher levels are needed to show the overall system. So you would show the higher level diagrams and abstractions to the users, to the stakeholders. The lower level ones to the implementers, to the outsourced people that you've hired to build this particular project. Two approaches might exist: the model and the entire system at the same level of abstraction, but present diagrams with different levels of detail. That's what you're doing for your projects. You're doing the first approach. And the second approach might be model parts of the system at different levels of abstraction. That's what object orientation aims to achieve. It takes different levels. For example, the sequence diagram or the activity diagram, only showing you activities or sequences or states or something. not showing you classes or objects or anything. But those classes or objects are in there. So object orientation is kind of, a step beyond looking at the big picture and then dissecting different levels of it. Instead, it just takes and separates out the big system into different levels, and you look at each one of the different levels to get an understanding. Which is why you can kind of put them both together and get the best of both worlds, essentially. So, and here's an example of a component diagram. This is a high-level diagram. This is Hello World. So we have the Hello World HTML page. It's an applet for Hello World HTML page, and we've got the class that was written from the source code, and we've got a picture that shows up. This is Hello World with a graphic picture on it. So, and this is, believe it or not, you'd think, well, it's Hello World, but if it were a huge system, you might not know which component works with which other components. You might not know that this HTML document has this graphic and it also has this class on it. So, obviously in a more complex system, it would make better use. And we have the actors and the use case diagrams that we've seen before. This is kind of a summary of the techniques that we've seen so far. The actor here is the user of the system playing a particular role, and the use case is the task that the actor is actually performing. So we have a borrow a book task. We have a book borrower in terms of the actor. And we put those pieces together and we create scenarios out of it. It gives us yet another lower level of detail on the component. And it's going to show us something completely different than a component level. So the scenario is an instance of the use case, and the actor is the role, not an individual. So it's kind of like entities. It's kind of like going back to the entity concept. The object concept. Librarian can have many different roles, can do many different things. And the actor must be a beneficiary of the use case, hopefully. Must be part of the, receive something or give something. And in UML, the system boundaries is the set of use cases. So if the use case crosses over into another system, then we have an integration diagram that we look at. And we say, well, how does this system integrate with that system? And then because we have to look at interfaces. We have interface diagrams as well, which makes UML more complicated than you could possibly imagine if you think about it. And I'm standing here saying it's complicated. It really isn't. What's complicating is that there's so many different types of diagrams. It's finding the right diagram to suit the needs and making the diagram look like it's supposed to look in terms of the type of diagram that you're using. I see a lot of component diagrams that look like object diagrams, that look like use case scenarios, that look like, a bunch of other things, and I look at the diagram going, what is that supposed to be? That's the confusing part. There's too many choices. It's kind of like learning how to program in a language that gives you multiple different ways of doing something. Which way are you going to do it? So too many choices gives you too much adds confusion to it. So here's the use case of the borrowing of a book, where we have a book borrower who's going to extend a loan and borrow copies of books, essentially. Relationship between use cases here with the uses relationship. The book borrower extends a loan and uses a check for reservation. Uses this, so we can put uses in there. And we're basically looking at kind of a hybrid use case scenario and entity relationship diagram. Think about it. But we're not showing relationships, we're showing associations. So. And then we have the extends, where we have the book, the activity of the borrow copy of book that is extended by a refuse loan. So in terms of the development cycle, the use cases are actually kind of important because they're used in a lot of different areas. They can be used right from the beginning to solicit a requirement to figure out what it is we want to do with the system, and then also communicate the requirements back to the user. It can be used in the analysis and in the design to figure out the scenarios, so we can map that out, make sure we're implementing the correct behavior in the system. It could be used in testing to figure out, well, why are we testing? What are we testing? And then how many, basically how do we create the test cases? Well, we can take the use case scenarios and turn them into test cases, so we have at least hit the major functionality of the system. So we have a tool and requirements analysis, easy to discuss to clients, often hard to translate into class models. So we don't have diagrams that can actually easily translate from one to another, which is the other interesting part about UML as a side point as well. Not only do we have a huge variety, they don't translate very well. It's hard to take a use case scenario and turn it into an object diagram or a class diagram or vice versa. So, but you get that in a lot of different languages as well, or different methodologies, I should say. Scenarios are also useful for validating designs and for validation testing. So, who's this in the background? I don't want to do updates right now. Just make sure I'm still recording. Good. Alright, so that was kind of the conclusion of the object-oriented design stuff that I was going to give you. It did give you. If you really want to learn about object-oriented analysis, take an object-oriented analysis course that just focuses on that. That's not very popular of a course these days. It's usually combined with a programming language, and it's usually turned into object-oriented design instead of analysis, because nobody wants to sit around and analyze stuff. They would rather implement it. They would rather design it. So, you know, object-oriented design would be your next course, I guess, if you were really interested in that. So let's take a look at UML versus entity relationship diagramming and kind of conclude with the big picture in terms of what we're doing in terms of our analysis and our design, because this applies to both concepts. So UML is not and can never be a replacement for entity relationship diagramming. It doesn't replace it, which is the common mistake a lot of people do, especially when they assume that they're going to implement their project in an object-oriented methodology. Or, you know, it's going to be a Java platform item. So you can't skip the whole structured analysis and design and just go directly to object orientation. And theoretically, a lot of people are under the misperception that they can, and that causes faults in the design process and makes the design analysis and design take twice as long or so, because eventually they have to go back and start from the beginning. So, not a replacement. And despite the advantages, it's not without its own weaknesses. It doesn't show a lot of stuff that the structured analysis shows, which is why we use them both in combination. And in some ways, UML diagrams are more symbols, making them more cluttered, therefore less easily understood by users. Believe it or not, even those use case scenarios with the actors and the actions can be cluttered to the point where they don't make any sense either, even though they have these nice, cute little, stick figures on them. They still can be very confusing. The class diagrams in UML are a superset of the entity relationship modeling. In fact, we've seen the object and the class diagrams are a superset. And there's nothing that can be expressed in entity relationship diagrams that cannot be expressed in UML notation. But there are many more structures and relationships possible in UML that cannot be expressed in entity relationship diagramming. So start out with ERDs and move to object-oriented design, and then you're working in a good order. You can't work backwards. So let's take a look at see the shift and how the terms kind of correlate. We have an entity, which is actually the class. The instance of an object, instance of an entity is the object. So, in fact, this is the same terminology they teach you in the object-oriented design courses. They say, we implement an object by a class. So an instance of an object, when an instance of the object creates, we actually create the object. The object doesn't really exist until an instance is created, which is how an instance, and we do have instances, we have entity instances, because that gives us our cardinality in the entity relationship diagram world. So we have entities and we have instances of entities, which roughly translate to an equal kind of comparison. We don't have relationships in UML, but we have associations, and we don't have associations. And people, often kind of are sometimes confused about the differences between a relationship and an association. It's like, I always think of it as like, are you friends or acquaintances? So, if you're an acquaintance, you're an association. If you're a friend, you have a relationship with that person. So, we can kind of think about associations for a second and say, yeah, I know all of you guys. I'm associated with you. You're all taking my class. Do I know any of you personally? Some of you maybe, some of you no. So, but we have a connection because you're taking my class. So I have an association, but it's kind of a weak relationship. It's not a full, like I know where you live, I know your contact information. Better yet, I know your names. That might be stretching it for everybody. So I know some, but I can't remember everybody's name. So in terms of the relationship, that's what we're showing. Entity relationship diagrams are showing those strong relationships. So this student takes a class. We're assuming that there's a relationship. There's a lot of assumption that goes on in an entity relationship diagram because we're translating those associations into full relationships. In a UML term, we can take and we can show the role of the association, which we don't have any roles in entity relationship diagram. The concept doesn't exist. Because in terms of an association, we can say a student enrolls in classes, or a student audits a class, or a student dropped a class, or a student added a class. We're showing so many different types of roles in terms of the association between the student and the class. We would have to show all of those as separate relationships, which takes up a lot of room in the diagram, and it makes it complicated. Because we're not really, and are they really relationships? Does the student have a relationship with a class if they dropped it? So this is a lot more expressive and a lot more flexible and a lot more confusing in the long run. So attributes are attributes. That's the same thing. So classes have attributes, so do entities. They both have attributes. So in terms of mapping it, any entity relationship diagram can easily be mapped into a UML diagram. Well, two classifications. It can be an object or it can be a class quite easily. It also actually does translate into other ones like activity diagrams, depending upon the nature of the ERD. Many structures that cannot be represented on an entity relationship diagram can be represented in UML. UML does states, it does sequences, it does behaviors that entity relationship diagram doesn't do. And in entity relationship diagrams, there are two sides of the relationships to name. And in UML, you also have the option of naming the two sides, but you also have the option of placing a name and a direction on the relationship itself, meaning that, the student drops the class, and the class doesn't have anything association with the student outside of that, and that the student is the one who's dropping the class in terms of the action and the association. So in the UML, ends of the relationship are called the association roles, as I mentioned before. So here's the roles in UML, and here's another example of a person who works for a department. And we have an employee and employer. So between the department and the person for the employment relationship between the two, the full UML notation would look like this. And it's really showing an association. Because do you really have if you're an employee, do you really have a relationship with the department, or do you just work for the department? The department is a concept. It's a group. It's a gang. No, it's not really a gang. Actually, some companies it might be, but it's a grouping. And so the person, many employees, works for, and then we're showing the department in terms of the works for relationship as the association, and then we have employer. So it's very common to see in a UML diagram, although this looks like an entity relationship diagram, and it's a UML diagram because it's showing the employee and the employer. The classic way of getting around this problem, and you say, well, I want this to look like an entity relationship diagram, is to put that diamond symbol in here, take away the arrow. And then you wouldn't normally put the role names on here either. So the department acting as the employer may employ many number of persons as employees. And you might be thinking, well, in this particular case, it is just a notation. The syntax is the same. So the notation includes the role, and each one of the objects in the class is assuming the relationship that's expressed. And entity relationship diagrams do not show or do not include the role information. So that would actually be improper to put the two roles on here. And the relationship itself is expressed by a verb. Well, it's the same thing. The relationship is a verb. Students take classes in an entity relationship world. So it holds up fairly well. And sometimes it's difficult to determine the appropriate word, obviously, especially when you have multiple roles that are going on. Do classes take students, or do students take classes? So takes, is probably not a good word to use, but enrolls in. Has, maybe student has classes, classes has students. So it's kind of tricky. Same problem you have in UML. So if you're creating abstract models with the same relationships, might represent more than one type of an association, the naming becomes somewhat more complex, as we've seen in that kind of similar example. And here are two diagrams that are compared, which are kind of interesting. And we have entity relationship style representing a many-to-many relationship, where we have a student and there's an enrollment, maybe an academic transcript or something. And on the academic transcript or the enrollment, we have course offerings that are on that. So one course offering might be on many different enrollments. Many different students might have many different enrollments as a concept. This could be like, I don't know, enrollment documentation of some sort. And in the UML diagram here showing the same thing, where we have enrollment history, duplicates allowed in terms of the association, and then we have employee and department as an example that might have employment. I said enrollment, employment history, that's a part of. And this dotted line is saying that this is an attribute, or it's a weak entity that wouldn't exist if we didn't have this relationship. Looks kind of similar in terms of diagramming, especially when we leave out those diamond symbols. So diagrams look very similar. It's kind of showing the same thing in different ways. Now, recursive relationships are a little different, however, in terms of their representation. You can actually show a true recursive relationship in UML notation that you can't really do very effectively in an entity relationship diagram, because in an entity relationship diagram you're not showing roles or associations, you're just showing relationships. So all you can do is say that a person has a relationship with the person. This could be staff and managers, or employees and managers or whatever. So in UML, you can explicitly constrain the relationship very precisely. So we have a recursive relationship on the class employee, and employee can be indicated by the constants, by essentially the two different roles here. So we have a person who is an employee managed by a boss, and so we have two kind of classes in a tree that we can line up and just overlap them essentially to show that we have two different roles. You can be an employee, or you can be a manager. You can be a boss. So we have the person and the boss, essentially. It's not really two separate components because they're overlapping. They are together in terms of one, they switch roles back and forth. So it's basically showing you the roles. We also have components in the UML diagram. So in this particular class diagram, comments are graphically represented. This is the notation. These are just examples of some of the things we've seen already in terms of the notation. This doesn't exist in an entity relationship diagram. Do not put comments on your diagrams. It'll look like part of the diagram. But that's supposed to be like one of those post-it notes where you take this side and bend it over, stick it on something, stick it on the refrigerator. So what we're doing here is we have a text object here that is attached to the UML diagram. No comments in entity relationship diagramming. The naming of the associations is pretty much the same as the naming of the relationships, except for we have many different associations and we only have one relationship. So rather than naming both sides with a verb phrases in terms of the entity relationship diagram, in UML we name once and we put a directional arrow that is added to tell us which direction we want to read it in. So it usually points to the many side of the one relationship. So employees work for a department. And here's the interesting phenomena, and some of you, usually a couple people at this point, start looking at this going, wait a minute. You've shown me entity relationship diagrams with arrows like this before. And I have, actually, in a couple weeks ago, I showed you entity relationship diagrams with arrows and names. Here's what's happened. We've worked backwards. It's very common these days. In fact, this is why, if you've seen any of the older entity relationship diagrams, the attributes are always outside of the objects and they're like in little bubbles. And then now, all of a sudden, the attributes are now inside of the entities. Oh. Well, that came from a UML notation. When all of a sudden we started having classes with those 3 different sections in it, identity, states, and behaviors inside of a class box, all of a sudden now the entities look like classes. And then in the old days there was a diamond symbol that was used for the relationship. The diamonds are almost gone. They faded. They were originally introduced because we could show different degrees, 3, 4 participating entities all in the same relationship, and we'd have like a line to, you know, smoothly attach all of the different entities. We still see them used for that purpose, but when there's a binary, one entity that has a relationship with just one other entity, the diamond generally goes away. And then the notation goes to a UML style sometimes. And in fact, some of the tool sets for entity relationship will show you UML notation, which is kind of interesting. So we're kind of fading the line between entity relationship and object or class diagrams. So it depends on how you learned how to do it as to what symbol set you're going to use. But the interesting thing is although we are creating an entity relationship diagram, we're using the UML symbol sometimes, and then we're not showing UML because we're not showing the associations, we're showing the relationship instead. So the diagrams themselves, my point is that the diagrams themselves can be extremely confusing to look at, which is like you can look at this and go, if I change the label, took UML off of here and put entity relationship, move this arrow to the center, it would sort of look like an entity relationship diagram, modern day. This one's never going to look like UML though, because we don't have crow's feet, and these should really be rectangles, they shouldn't be ovals. And here are the employee that works for a department, so many employees, this is supposed to be crow's feet, work for one department, so it's an employer of a department. And here is the same idea, but in different concept. But most of our modern day entity relationship diagrams are looking more like that than they were from the beginning. So the notation style is definitely upgraded itself with the introduction of object orientation, which makes it confusing. And again, there's no standard in entity relationship diagramming either. It's not a standardized concept. So without standardization, we don't get consistency. Nothing has to be a certain way, so people have their own ideas. In essence, you could actually be doing object-oriented analysis and design, but still thinking in an entity relationship structure, but never creating an entity relationship diagram if you start out with the class diagram or the object diagram. So, generalization, interesting concept. It exists in UML, does not exist in, it's more flexible, but it does not exist in entity relationship diagram. So it's more flexible than the relationship. So in entity relationship diagrams, all we have are entities, relationships, and attributes. So UML, we have associations instead of relationships. But we also have generalizations. And then we have different characteristics, so associations and generalizations. More often you'll see the association versus the generalization, but it's basically all replacing the relationship concept. So there's not, there need not be only one generalization structure for a given particular class, so you might have multiple generalizations that are operating on the same class. And here's a classic example of what you can do in UML that you can't do in entity relationship diagramming. So a consulting contract, which can be time and materials or fixed cost and independently classified as a government or private. So we got government, private, fixed cost, or time and materials. Let's look at the UML as an example. This is a generalization, meaning that it can be a fixed price or it can be a time and materials costing. Or the origination type, not the billing type, but the origination type. And these are two generalizations, and you'd label this, generalizations. You'd label it, billing type. You could put the word on there, or you could leave it off. It's classic just to see it left off. And then we have private and government. That doesn't necessarily mean that we have a relationship between both. We have the option of full or partial participation or no participation. So If we were to do the same thing in an entity relationship diagram, we can't connect any dots. This would be a rectangle with rectangles inside of it, or a bubble with bubbles inside of it, but the problem being we can't show the generalization. We have to show that there is a relationship. But there might be a contract that is just fixed price, that doesn't use time and materials. So, long story short, we can't really show it because the tool set doesn't lend itself. So when you're basically looking at generalizations or associations, you take the UML route. And if you're thinking along those lines, you're probably looking at an object-oriented design anyway, because otherwise you would not be using that type of terminology. So beyond entity relationship diagramming, UML allows the creation of all sorts of different types of general entities, class relationships, associations, all sorts of different things above and beyond what an entity relationship diagram is going to show you. And here's another example in terms of what it contains. We have interaction diagrams that we don't have. And I'm not going to go through, and you don't actually have to create all of these diagrams. You have to create a component level diagram, and you have to create, or actually it could be made from your entity relationship diagram. So you have to do a data flow, an entity relationship, and then one UML. And this is true for both the analysis and also the design document. And if you want to, you could do an interaction, a sequence, a collaboration activity in one of these other diagrams. And we'll take a quick peek at these to see what they look like. But I'm not going to go through all the different diagramming techniques for it. In fact, once you learn how to do diagramming in general, they actually kind of just, they're just different variations. You get the tool, you get like a Visio or something, or you get a tool set that works with it, a rational rows, or one of the object-oriented analysis and design tools. And they have templates, so you can see pictures of what the diagram is supposed to look like and drag and drop the symbols. So an interaction diagram is a set of objects and relationships, including the messages that are dispatched among them that go back and forth in terms of the interaction. Interactions could be sequence or collaboration. Sequence, the time ordered of the messages. The collaboration might be which objects are sending and receiving, which objects are working together on something. In terms of the activity, we're looking at the flow of the control from activity to activity. And then we have the state chart diagram that models state machines. So here we can show actions on objects, and these are the same symbols that are being used in all of the different types of these diagrams. So the call looks like a method call with a parameter in there. Okay to borrow, and then comes back and says okay, like a return call. It's return a status of something, and so most of these are arrows. They create the destroy, showing you an action in terms of the behavior of the association. Send, modify, return. So here was a UML that can show a link between a library member and a copy of a book. So again, we're looking at a class diagram, but we're looking at the link between the two classes. And so this is the same example that we looked at in the last lecture, actually, with the borrower in the library. And we have a lot of this notation here is put here to kind of document or to show you what it is, label what it is you're looking at. This is an association, so we have a copy of a book that's on loan, and the library member said we could borrow the copy, or you're going to return a copy. So the library member is working with this copy of this book that's on loan, and showing you the relationship or the association between the copy of the book and the library member. Now, the copy of the book might have a relationship with the person who borrowed it, but they have an association with the library member. And then we have the library member, which is the object, and then we have the copy, which is an object, and then we have a message that's being sent. So that's why we have these arrows essentially showing you the link between the two, which is like, explaining the line concept. And then here's the sequence diagram of kind of a similar scenario, sequence numbers added to messages. So we have one, or we have a get name. It goes to the engineering student object and gets the name of the engineering student object. So we're running a method, essentially. And then it returns the name. So in here are the sequence numbers, 1, 1.1, 2, 2.2, 3. They're just basically showing you the sequence of the exchange of information. And then In the second exchange, a new student is created. Think of these as method calls if you want. And when you run new student with a name to create a new student, it goes out to the student object and creates a new object. So we have the creation of a new object. And then here's item number 3, might be, destroy the object. After we created it, why we created it, I don't know. Why we destroyed it, I don't know. And the sequence is going to be basically show you what happens when you send a message to an object, and then what gets returned from the object. And then what happens when you send this other message to another object. It's not really showing you the collaboration, not showing you the classes, but it's showing you the sequence of events when running methods. Here's a sequence diagram for borrowing a copy of a book. So we have the library member over here, library member object, the book object, the copy object. And so the method to borrow, so what are you going to borrow? You're going to send a parameter of the copy. And it goes to the library member, and it says, okay to borrow, okay. And then borrow, then, if we're okay to borrow. So there's a check here that says, and this is kind of like a data flow diagram in some ways, but it doesn't look like a data flow diagram because we have process bubbles that appear here, and these process bubbles are kind of doing the logic. But rather, instead, we're showing the sequence. So the borrow method sends something back and says, okay to borrow, not okay to borrow, because maybe the user's has like a ton of books on loan already and hasn't returned anything, and the library member's not going to let them borrow something again. And then borrowing, if it's successful, as an example, the copy. Is there a copy of the book available? Because there's not just one book in the library. There's many different, like 5 different copies of the book. And so the copy is going to go, well, is it borrowable? Then go to the actual book. It's kind of like when you buy something online, say, hey, there's 5 of them in inventory. Okay, go get one. Until they actually find it in inventory, you can't buy it. But the system says there's 5 of them. So this is kind of like the same process of showing the sequence of going from a copy to finding the actual book. So. And you can see you can't do this in entity relationship diagramming or data flow diagramming. It's not showing you the sequence. Data flow, as I mentioned before as a side comment, you could turn this into, I could not really turn it into, you could create a data flow diagram that would show similar processing. In this case, we would have process bubbles that said, process the request to borrow a book, process the request to borrow, and then return the book. And then all of the activities could be diagrammed out. Here's a class inheritance diagram where we have an interface, and then this might look familiar, and maybe not, it doesn't have to. But these are all of the inheritance. Everything in Java comes from object, and then we have component, container, panel, and then applet is part of panel. And hello world is part of applet if we were to make it an applet. If not, we'd make it part of panel if we were going to do some GUI application development. It's basically showing you each of the classes in a sequence, and obviously the list was too long to fit on the slide, so we had a arrow going this way, which is kind of common. You'll see a whole page of it going this way. Or you'll see it in really small print, kind of next to each other. How you do the diagram's up to you. Here's an activity diagram using a process model. Kind of a hybrid between a data flow and an entity relationship, but it's not really showing any entities, it's only showing the data. So I would think of it, this symbol kind of tells me it looks like an entity relationship, but it's not an entity. So it's more of a data flow, but it's not really data flow either. So it doesn't meet any of those entity relationship equivalences. So what do we have? We have a process bubble. Well, we see those in data flows. Release of the work order, going to another, materials not ready or materials ready, a decision. So this is more of a decision in terms of an activity diagram. You can think of this more like an old-fashioned flow chart. Is it going to go this direction or is it going to go this direction? And you could have used, this is the same decision symbol that was used in the old days for flowcharts. So. If the materials are not ready, then reschedule it. If they are, then assign some tasks. So just showing you the flow in terms of the processing. And then we have parallel activities. Try to show this in an entity relationship or a data flow. It doesn't work either. And what are we looking at here? We've got a start state, and then we have a decompress. Okay, we're translating video or audio, multimedia, converting it. So we have let's maybe just call this a DVD. We have the video stream, and then we have the audio stream track of the DVD that we want to do something with. We can fork off an event to say decompress it, and then we can take this stream, take that stream in parallel, do some processing on it, and then put it back together, join it together for the final state, which is going to be the outputted translated file. So if we were ripping it, cutting it, to translate it from one format to another or something, we would have to go through something like this. We would actually have to go through this to play it too, actually. The audio and the video get separated out in terms of the live streaming of the content. So sometimes you turn on the TV or something. Usually happens with digital cable for some reason. The audio track makes it there faster than the video or something, or than the stream data track, and then the words don't match the person who's talking. So. Straight state diagram showing you the state of a class book, and here's a state in terms of is it borrowable. It could be borrowable, and sitting here in kind of what would be called a state machine kind of state, in which the book, borrowable books just sit there. It's kind of like, items in a store, kind of just sit there waiting for someone, kind of a wait state. And then if it's not borrowed, it could go into a borrowable state, and then it kind of goes back and forth between being borrowed and then not being borrowed. Kind of like a network protocol, or a network activity software that sits there and listens for information that might be coming through on a port. If it finds something, it does something, and if not, it just sits there and waits. So you can't diagram that in an entity relationship or a data flow diagram either. So, in terms of UML models, in terms of implementing them, we have subsystems, and then we have component levels. So in your analysis and in your design document, it says you have to give me one component UML diagram. It's just a term. A component is basically what we're talking about in terms of subsystem. So these are actually kind of the equivalent. A subsystem, which is the entity relationship diagram term, is the grouping of the elements that specifies what part of a system should do in terms of each one of the different elements or subsystems. And a component is the distributed place of implementation of the system, including software code, binary executable code, any kind of piece of the software, which is a component. So in your diagram instructions, it'll say one component UML diagram. Anything. It means substitute the word component with subsystem. That's why I said you can create an object diagram, a class diagram, a sequence diagram, anything, because you're just showing me one of something in terms of the component. So a component can be thought of as an implementation of the subsystem, if you want to think of it that way as well. So. Project work. Have I already gone over the analysis? Yeah, I've done the analysis document already. Have I already gone over the design document for this course for you guys? No? Let's do that. I have a few extra minutes. Let's revisit the concept of homework. Projects. Alright. As this is loading. So, a few weeks back, you decided on a topic. You created a requirements document, maybe, hopefully. At this point, you should be almost done with your analysis document. And you should be thinking about your design document. Okay. Actually, it's not a bad idea to even start working on some of this stuff, too. And as I mentioned before, the requirements is a standalone document. The analysis and the design sort of work together. The analysis is the rough draft of your design document. And the analysis, oops, I skipped. The analysis document is on page 46, I believe. 47. And the design document, let's take a look at both of these actually, is on page 75. So somebody remember 75. I'm going to go to 46 for a second and just briefly review, because some of you guys started the class late. Lo and behold, on page 47, we have the analysis document template. I'm not going to go back as far as the requirements. You can watch one of the older videos and get the requirements information. We had section 1, if you remember, was the introduction. Same repeat of your requirements document, essentially. Giving out any specific project objectives, overall requirements, constraints, assumptions, stuff like that. The interesting part of the analysis document was Section 2. Section 2 said functional requirements. And in here, if you read the description, it sounds like a lot more than what I've been saying. It is. So, the entity relationship diagram. So, you want to create an ERD showing all of the entities involved in the entire scope of the project, not just the prototype. So all of these documents, the focus of the document is the final product, although you're not going to be making it. The database, yes, the entity relationship diagram does lead to a database design, for those of you who have not taken the database course. Delivered with the prototype must be consistent with the ERD. If you're going to deliver a database, you do not have to deliver a database with the prototype. The entity descriptions in a narrative format that clarify what each entity represents to someone who might not be familiar with the business rules that are being modeled, or the area that's being modeled. You can leave that out. You don't have to include that. Attribute definitions for each of the attributes, you don't have to do that either. You don't have to put in narratives for the entities or narratives for the attributes. And should include length, data type, possible values. No, you don't have to do that either. So you can strip all this out and say, she's asking for one entity relationship diagram. Data flow diagram. Let's talk about that for a second. Must cover the scope of the entire project. Okay, well, same as before. Must include the contextual level diagram and one or more lower level diagrams as needed to represent a process bubble for each major process within the entire proposed system. Give me one diagram if you want, at least one. You can give me more if you want. What this is asking for you to do is to create process bubbles for everything. So if you do one and it has all the processing in it, great. If you want to do multiple, you can separate it out. You don't have to put it all into one. It might be easier actually to create more than one data flow. What I'm looking for is give me a list of your processing, and then, because underneath it, each process is going to be described. So it must include a primitive level process bubble for every process in the working prototype or the system. It's going to be hard to get the entire system when you're thinking about just the prototype. And no, you don't have to implement these processes in the prototype. You do not have to implement anything in the prototype in terms of this. So consistent with the data between the levels must be maintained. No more than 9 processes should be present in any given diagram. So that actually kind of holds true. That makes it less complex to actually look at it. So bottom line, give me a data flow diagram, at least one, and show the processes. And try to show as many processes as you can, essentially. If you give me just one process, it's too trivial. So, the next section, you're taking your processes that are in the data flow diagram, and then hopefully you've numbered them out, and you're just giving me a description. So that you do have to describe, and that comes into the concept of process descriptions. So each process on every data flow diagram must have a corresponding process description. Process descriptions for primitive level processes must be supported by descriptions that meet the criteria for enabling blah, blah, blah. You can use structured English, you can use just plain old English. If you read it in the course notes that prior to this particular template, you'll see something called structured English, or you search on it. Like pseudocode almost. You don't have to use pseudocode, you don't have to use structured English. You can simply say, this process calculates if the book is going to be borrowable or not. Design specifications. You need to include a design architectural description. Just describe to me the architecture of the system. This works on the Windows NT. Oh, this works on Java platform. This is the identification of the development tools that will be needed and the hardware, software platform. Obviously, if you're working on .NET, you're going to need to use .NET. Microsoft, it needs to be created in the Visual Studio.NET. Or it needs to be created using the Java JVM environment. Keep the section brief. The next deliverable is the actual design specification document. So don't get elaborate, just 1 or 2 sentences. Just tell me something about the architectural description. would be nice to know that this was a .NET application, if this was a .NET application or something. And at the analysis point, you're kind of deciding what you're going to build it in. When you're, looking at the entities, looking at the data flow, you might say, well, this is going to be an Oracle reports application or a SQL application or something. Performance and reliability requirements, you may not have any. If you're building a heart monitor, I'd say you'd have to have 99.9% performance and reliability. If you're building a ATM, perhaps reliability would be good. I don't know, security might be good. Component and deployment diagrams. You need to provide representation of the hardware software components in the UML format. This is where you're putting in your one UML diagram. So remember I said before we need one UML, one entity, one data, one entity relationship, one data flow diagram, one UML diagram. This is, and I called it a component/deployment. Means you can create, just scratch this off and I just make it just a component. Because component and deployment, deployment is going to show you more of a contextual diagram. Component is going to be anything. So something either about the creation of the system or the implementation of the system or the system running in terms of its context. Any UML diagram. You could put a use case in here. You could take your entity relationship diagram and translate it into an object or a class diagram quite easily. Stick it in this section. The test plan. I believe the test plan is included in lecture 11, but let me just... Testing. I'm going to talk about the test plan next week. So you'll have that little piece of information that you're going to need to develop the test plan. So hold on to that section. Not that anyone's even here yet. But if you are here, hold on to that section. So what page am I supposed to go to? 75. I remembered. So that's the end of the analysis document. You put that in a Word file. You can, Word file if you want. You can have it separate pieces if you want. If you did it by hand, you can do it by hand if you want. Staple them all together, give it to me in person. Or it's probably better if you just scan them into a computer file and you can upload them to the EMS correctly. So on page 75 we have our next deliverable, which you should be able to make as well. And what do you have to do with the next deliverable? Let me find page 75. And by the way, there's a ton of stuff in here in the course notes that might be pretty good reading, actually, about coupling and cohesion and stuff. Functional decomposition, all sorts of different topics in this document. Lo and behold, our design specification requirements. Here's our template, starting on page 76. The other one was on page 46. I don't know. Anyway, numbering is one page off on both. So, you have this beautiful analysis document that you've just put together, and it's your starting point. You take that document, and you build it into the design document. You reuse everything. So what are you going to do? Section 1 is pretty much the same as your original section, but you're going to add to it a little bit more. Take your original introduction section and add the goals, the objectives, statement of scope, software context, major constraints. You can read through this stuff. It's fairly self-explanatory. If you do have questions, you can certainly send me an email message and let me know. But it's a pretty much repeat of your last introduction section. And in the design document, you can keep the same numbering, except for 2.0 here it was before functional requirements. Now this is going to be data design. And 3.0 is going to be architectural and component level design. And 4.0 is going to be user interface design. User interface design. And then 5.0, we have 5.0? Yeah, restrictions, limitations, and constraints. So we've taken 2.0, we've stretched it out. And we've stretched it out, and now we have, let's look at the data, let's look at the processing, let's look at the interface design. User interface. So we start with the data because that's usually kind of the easier component. And we have an entity relationship diagram that we put together. So we take that and we look at the internal software data structures. So the data structures that are passed, or the data that is passed among components of the software described. and the global data structure is created, and it might be available for different parts of the architecture. We might have temporary data structures. We might have a database description. So the last part of the database design is what your entity relationship diagram is going to give you. You read the diagram, and if you're taking the database class, it's quite easy. If not, guess at it. Take each one of the entities, turns it into a table, take the relationships, turn them into tables, and translate and kind of come up with an initial design. Whether your design is correct or not, it's not really going to matter. Because most of the time, it isn't. And the implementer has to fix it anyway. Or this is only the first draft that you're creating of the design document. By the 7th or 8th draft, it might be correct. But you're only giving me one draft. It does not have to be perfect, is what I'm saying. It's not going to be perfect. So that's the last section. But prior to, in 2.1, 2.2, 2.3, you might have log files. It might not, all the data might not go into a database. You might have, how many systems have like log files, history files, temp files? That's what you're discussing in terms of all of the internal support. So think about all the data components that your system might actually use. And this is not the prototype, this is the real system. And describe to me in these different sections. If you don't have one of them, leave it out. If all you have is a database and your program is not storing anything to a text file, it doesn't have any temporary data at all. I'm sure that was kind of rare actually, but in some cases it might not have any data. If it's not running on the internet, it's probably not going to have any session data or anything. It's not going to have anything. Then leave it out and just give me the data that your database contains. If you're building an application that doesn't use a database, don't put a database design in here. So this is going to be very particular as to what your system's doing. In section 3, we have the architectural and the component level design. And in here, we are doing an architectural diagram. It's a pictorial representation of the architecture that is presented. Here's why I'm showing you the design document right now. Because you can reuse everything from your analysis document, which means you could create a UML component level architectural diagram if you wanted to. If you don't have it in your analysis, you have to create it. It has to come from somewhere. But what we want in the 3.0 section is our component level design. And our architectural design. We might actually have the component level design already in the analysis document. If for the UML component level diagram, you created an object diagram or a class diagram or some sort of an architectural diagram, you can reuse it. So most of your work's done in terms of that diagram, hopefully. If not, what you want to do for section number 3.1 is you're describing the program structure chosen for the application. This is that section in your analysis document that said you were going to use .NET, or you're elaborating on it. You're taking that, oh, this is going to be a .NET, or this is going to be a Java application. This is where it comes into play in section 3.0. You're describing that in a little bit more detail, and you're providing an architectural diagram. So you can reuse, you're not going to have to reuse your data flow or your entity relationships, but you can reuse that component, that UML component diagram. And then any alternatives is the next section that might exist. There might not be any alternatives. You could put no alternatives. Or let's say you're building it in .NET and you have this architectural design. You say, well, I could totally do away with .NET completely and do this on a Java platform instead. And I'm using .NET and Java kind of as a comparison only because they're middleware platforms. They're kind of similar, but they're way different in terms of implementation. So after you give me the big picture, which you already might have, then you give me, in section 3.2, we have description of component N. So maybe you have 4 components in the system. You give me 4 different sections. Description of component 1, 2, 3, 4. So you break it out into each one of the different components that are in that component diagram. So that's why I say do like a class diagram. You can give me all the different classes. It's module diagram, all the different modules. Object diagram, all the different objects. Any level of abstraction you want, you can actually use for this. So the detailed description of each one of the software components containing within the architecture of the system that's presented in your picture. So in your picture you can label them 1, 2, 3, 4, or you don't have to. You can just say description of client, description of server. Let's say you only have 2, client and server. Description of client, description of server. And so what you're providing for each one of these is a narrative, a processing narrative of the component that's presented. As an example, description of component server. The server shall accept client connections, and the server will give each client a file, and after it runs a query on the database, it's going to deliver this file, and the file is going to contain X, Y, and Z. And only one client can connect each day, and multiple connections will be rejected, and anything that the server behavior might actually be doing. And then vice versa for the client, description of the client, description of the peer, description of whatever component you've identified. So you've got a basic little narrative, and then a description maybe of the input, the output, the interfaces. The client sends a name and a password to the current, I want to say kernel, to the server. The server sends back a confirmation message to the clients. So any inputs and outputs and stuff like that would be in the component interface description. And then the processing details, any algorithms, anything. If you don't have any processing, you don't have to worry about it. And in this section you have processing of interface design, algorithmic model, restrictions, limitations. You may not have any of this stuff. These are just suggestions as to what would be included in this particular section. And then we also have the software interface description for each one of the components. And if you notice here, 3.2 starts out component, 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 component. 3.3 is software interface description. It could be for all of the components together, because the interface description is going to say how are these components working together. And let's say it's on an external machine interface. So let's say we've got external system interfaces, maybe human-computer interfaces to it, maybe it's data. So software interfaces to the outside world are described. May also be internal to the system. Depends on what kind of interfaces you have. Usually, if you're running, let's say, an internet application here, the interface might be, it runs on the internet. And external machines might be computers, devices. Described must have a router. Must be connected with, hopefully a broadband or something, speed. And it's going to be very particular. You might not have any external interfaces. The system might run on a network by itself, not work on an internet. Might not even work on a network. Might just work on a single computer. Then this section is going to be extremely small because you're going to put down there no external interfaces. So if you have any external interfaces, this is where it goes. And it goes for everything, not for each one of the components individually. And then lo and behold, the last section is probably the most entertaining. It is the user interface design. Not too bad. A description of the user interface design of the software that's going to be presented here. Description, you can do screenshots, screen images. This can also be your prototype. I haven't talked about prototyping yet. It's coming up right after testing. But what we're essentially doing is drawing something out. We can create drawings, pen and paper. We could do it on a computer. We could bring up Visual Basic if we're familiar with that. Do the window motifs. Just put the windows out there and pretend like it's a fully running program. And do a screen capture on it. We could do HTML on here. Anything you want, given your capabilities, to mimic what the user interface screens are going to look like. So you detailed description of the interfaces, because we haven't really talked about, in terms of all of our documentation so far, we've talked about the data, the processing, but not the user interface. That's kind of an important concept to give the developer who's going to be reading this design document some sort of an idea about what the interface is supposed to look like. Obviously, it's not going to look identical to this, especially if you draw it by hand. So, interface design, interface rules, components that might be available, anything that might be associated with the user interface ends up in section 4.1. None of these sections require a lot of writing. you can just put a sentence. Here's the main screen. Here's a login screen. Here's a log out screen. And then you can save this stuff because this can be, taken out of this document and reused for your prototype. Because your prototype does not have to be a computer animated program or demonstration. It can be screenshots. So we're kind of working with the design and we're also accomplishing prototyping needs at the same time, actually. Because if anything, the user interface design that you're doing in your design document is sort of a prototype if you think about it. You're prototyping what the system should look like in terms of its look and feel. Section 5 is going to be extremely easy. You may not have any restrictions, limitations, or constraints. If you don't, leave it blank. Just say no restrictions, limitations, or constraints. Section number 6, we're not going to do section number 6. So you can scratch that off the list. That deals with testing issues. I'll save it for a testing course. We put together test cases. If you want to include them in your design document, you can, but you don't have to. We're not putting together a test plan. So the test strategy, the implementation. If this were a real true project and you were doing a complete design, well, you'd be doing more design work, but because this is just a partial sampling and that you're putting together for this particular deliverable. But you would also be including specifications for a test strategy. Because in the design phase, you'd be going, these are all the components. We're going to have to test the interfaces between the components. And we're going to have to test the use cases. And we're going to have to test, all of the different functionality. And we're going to have to trace all this stuff back to the requirements. And you can spend an entire course QA and testing. So better left for that because this is going to be hacked at the very least. So, and we're not getting into very much of in terms of classes of test cases and stuff like that. And then number 7 is going to be your appendix. So if you have anything for the appendix, great. You might have a requirements traceability matrix. You don't have to put that in there. These are all optional if you actually have something. Packaging, installation issues. If you're going to ship this on a CD-ROM, you're going to put it on a thumb drive, it's going to be available from the internet or something, you would go into this section. So you may not have any appendixes at all. It's optional. Questions about the format, the content, anything related to the design? See, the design is actually not quite as, it's not quite as much work as the analysis, actually. Think about it. All the time you spend doing the analysis, the more time the better, actually, because you're building a better design. You're just taking your analysis and you're putting it into the design. It's just hard to come up with components if you don't have any components. So if you skip the analysis completely and just go to the design, you've got no components to discuss. Then you have to actually do the analysis while you're doing the design. Well, let's have this component. Let's have that component. Let's have this one over here. So the natural translation of the analysis into the design is kind of the same activity. You're analyzing it and you're designing it at the same time, which makes the design document run a lot smoother, actually. And in the real world, you wouldn't have the analysis document. You'd have all of the analysis activities going on behind the scenes, but it's the design document that you're actually creating that you're going to deliver to the implementers and to show the customers and stuff. So. After the design, you have the prototype, and then you're done with the project. So we are actually kind of at the midpoint. We're at the mid part of this class right now, and some of you who were here last time probably would have noticed that I put the midterm out for this class. So it's not a bad idea, and I have to check with the TAs to see when the links in the EMS are going to be available. You can save up your project and turn it in all at the same time at the end of the course. All the deliverables you can post in one zipped file if you'd like. This midterm is right here. It's right underneath the syllabus. It's really easy, actually. It's not too hard. But it's not a bad way of testing to make sure you've got access to the EMS as well. I wouldn't wait till the end of the term to turn it in, but now's a good timing to start. Just take it, get that over with. And then it's a Word file. It's not too long. Then you'll have to upload it to the EMS. Does anybody know if the link is even there? Are you there? Link is not there. Can we work on that this week sometime? No. We should also, there's supposed to be a dedicated person now who's working on the EMS. If I could have you in charge of maybe perhaps telling that person to upload everything. That would be perfect. There we go. Got that taken care of. So I think we're done for today. Next week we're going to talk about testing. Remember, there's no classes on Monday because it's a 4th of July holiday. But Wednesdays, we're here again. So next week we'll talk about testing. Otherwise, I will see you next week. Enjoy your long holiday weekend. And sign the roster if you haven't done that yet.